Hello everyone. In this session, we will discuss how we build the solution to support multiple use cases at LinkedIn. The agenda for this specific session would be we'll look at system design, we'll look at how did we scale the solution, then we're going to look at how did we visualize our solution, and then we're going to look at some of the results. Let's get into the system design. So at the high level, what's really happening over here is on the top left, you have an optimization function which emits a probability density over the hyperparameters. This is a set of configurations we want to use in our online serving. Once we start serving the members these configurations, it will have an effect on how members interact with the product, which affects the metrics. And then what you have on the lower left side is we want to collect these metrics and call the optimization function again. And we want to do this in a loop. So there are a few realities about the clients who are using this optimization package. Every team within LinkedIn can have a very different online serving infrastructure. Like some teams use a streaming infrastructure, some of them may have an completely offline infrastructure, and some of them may have a REST endpoints. The second aspect is the tracking data and the metrics for each system can be very different. Even though we have a centralized metrics aggregation system for most of the metrics within LinkedIn, certain teams may still have their different calculation methodology. And so in order to make a minimum viable product and stay focused on solving the optimization problem at hand, we built this package as a library. And so let's look at how does a typical client flow look like. The client will call this optimization package in its existing Spark offline flow. And the client flow will really contain, at a high level, three flows. The first flow is a Hadoop or a Spark flow, which will collect the metrics and aggregate them. The second flow is really the optimization package, or which is basically the client product is linking with the statically linking with this optimization package, and what it will resolve into is a Spark flow, which will basically be a call to this library. And the third flow is basically going to use the output of this optimization package and use it in the serving system. So let's look at the overall architecture. The overall architecture has two main components. The yellow block is the library, and as you can see, it takes in the model specification. So we'll get into what model specification means. It basically is what is the optimization problem you want to solve, and so there is an API which we provide, and the clients can write that uh, write what is the problem that we want to solve. The rest of the components are built by the client. So let's start with the yellow block, and it outputs a PDF over hyperparameters, which gets stored in a parameter store, which we call as parameter distribution store. During the online serving for a member MI, we resolve the configuration, and then we fetch features and basically apply this configuration and show the output to the member on the UI. Based on the user interactions, several events are emitted and get stored in the HDFS. Then we have a flow which aggregates the metrics, and then we call the library. So the cadence of calling the library can be very different for different products. As you could imagine, a product like LinkedIn Feed, which has a very high traffic, you could do at a very frequent intervals, like maybe even 6 hours or 12 hours. For a product like notifications, where we do not have as much traffic, we would want to be a little slower. And the reason we want to do that is if you do it too fast, you're collecting less data, which means the variance in the data is very high, and that can affect your predictions. So let's look at a specific example for notifications, and then let's look at each step of this uh, flows so that we understand what's really happening. The problem that notifications team is solving is you want to send the right volume of notifications at the most opportune time to improve the sessions and clicks by keeping the send volume of notifications the same. So when you're comparing two models, you want to compare them by keeping the send volume of notifications same, and it should at the very minimum improve sessions or clicks. And we have the following two models, which will basically which basically is our machine learning models. Which the first model is the peak click, which is computing the probability of a click on an item I for a member M, and P visit, which is the probability of a visit for an item I and a member M. So, like we discussed in the previous slide, what we really have is a scoring function, which is p click plus x alpha p visit, and the decision function is p click plus x alpha p visit is greater than x threshold. So x alpha and x threshold are the hyperparameters that we may want to tune. And a business strategy, like we discussed, is you want to maximize sessions by keeping the clicks by keeping having constraints on clicks and having constraints on send volume. So let's look at what is the output of the optimizer, and we can walk back from there and understand every component in the system diagram. So the output of the optimizer in this case is a probability distribution over the configurations. And over here, what we show in the yellow box is there are three configurations that we are emitting, and with respective probabilities: zero point 0.3 for S1, zero point 0.5 for S2, and zero point 0.2 for S3. And if you look at the table below, it resolves S1, S2, S3 into what these settings mean. So S1 for over here is a threshold of zero point 0.1 and alpha value of 2, and similarly S2 and S3 respectively. So let's look at how do you resolve this PDF over the hyperparameters and assign it to the members. So you want to have some kind of a sorting criteria, and in order to do the member assignment, what you do is you run the following steps in a loop. So you have a the function assign parameter to the treatment members has a members array and has the density as inputs. And what you're doing over here is you're running a for loop over each member. First you hash the member and you get a value between 0 and 1, and then you perform a binary search to find the right parameter that you want to apply, and you append it to the member assignment array, and you return that back to the caller. So let's look at the example over here. So for example, over here on the left side of the table you have a member foo, and let's say after hashing it resolves to zero point 0.2. Now if you look at the right hand side, and if you look at the yellow table, what you have over there is S1 is what you will resolve to, because when you do a binary search, it will give you uh, any any probability which is less than zero point 0.3 will be assigned the configuration S1. And similarly for bar, when you hash it, you get zero point 0.7. And so now when you walk on this PDF, what you see is you will assign it to the S2 configuration, and S1 and S2, what they resolve to in terms of the hyperparameter values is shown in the right hand side table. So this is how you do the member assignment. Well, we're just looking at the architecture again, and next we are going to look at how do we aggregate the data. So if you look at the how the aggregation is performed, the left hand side table is a raw data of user engagement, and here what you see is there is a user ID, there is a parameter set which is a configuration, and there are raw metrics over here, like for example how many impressions, how many clicks, and how many sessions. So you, as you can see over here, maybe this data, this table on the left hand side is for a given day, and it is aggregated by user ID. So you have one record for every user, and now what you want to do is you want to aggregate the metrics by configuration. So over here we are showing you an example where we there are on the left hand side of the table you have three records as Foo, Bob, and Liz. They all have been assigned configuration S1, and in order to compute the right hand side table, you basically want to aggregate all these metrics. So S1 basically has an aggregation uh, data for which is aggregated by these three rows, and similarly S2 and S3. Let's look at the problem specification, uh, which was the input that is supplied to the optimization package, and this is where the client specifies what is the treatment model, what is the control model, how much you want to explore, how much you want to exploit, what are the names of these configuration parameters, and what is the search range. So over here what we see is it's basically we are showing it to you as a JSON. We really use Avro, but you know, for viewing purposes, it's almost the same. So you have a treatment model, which is the first line. The second input is the control model, and then you have the explore number of iterations. And basically, what exploration stage is the algorithm is exploring each point equally, um, and you really want to do this in order to, kind of collect enough data so you can start exploiting. And what you have over here is the control parameters, which the configuration parameters, where the field name is the threshold, and we want to search between 0.17 and 0.24. And as you can see, the configuration parameters is an array. So over here we are just showing you one, but it could be an array of multiple, where you can have specify multiple parameters. And then the second aspect of this is you want to suggest what is the objective and what are the constraints. So let's look at the objective first. Over here we are maximizing, and the name of the utility is click rate, and how you compute is uh, by dividing the click count by impression count, and you're specifying how you want to model it as a Gaussian distribution. Let's look at the constraint. The constraint, the utility name is sent volume by generated. And the way you compute it is by send count divided by generated count. And again, you want to model this as a Gaussian distribution. And there is an upper bound and a lower bound. And the reason we are computing this metric, uh, and we are dividing, like click count by impressed count, or in the case of constraint we are dividing send count by generated count, because we really want to normalize. So let's say if your treatment model has a traffic of 2% and your control has a traffic of, let's say, 10%, you really cannot compare clicks versus clicks. You really want to normalize it, and this is one way of normalizing. So let's look at let's just go over what did we talk about so far. So we basically have a tracking data. So all the member activities are tracked with the parameter of interest, which means the configurations that the members were exposed to. You basically track their member activities, and they get ETL'd into an HDFS store. The second step you do one does is you want to evaluate you want to basically aggregate the tracking data for a given configuration, and you want to store it somewhere. And this all of this is agnostic to what kind of problem you want to solve. And then is the third step, where you apply Bayesian optimization, where you provide the aggregated data and the problem specification, which we saw in the previous slide, to the library, and the library will then output a distribution over the configurations. So if you look at what the library is outputting over here is, you have a set of potential candidates that you want to try in the next round, and let's call them x1, x2 up to xn, and the library is going to output a probability for each of this, such that the sum of the probabilities is 1. And like we discussed in the previous in the few slides back, the way you resolve a particular configuration for a member is you do a binary search, and that's what we are showing. If the hash value of the member is between pi and pi plus 1, you will apply pi for the member. So the online system that we discussed, for a given member M, you can either do the resolution of the configuration offline, which was, we discussed, like we have a for loop which goes over all the members, and you do the resolution, and then you can use that resolved value by storing that resolved value in some online store. Or you can basically try to find the right assignment in an online fashion. So the only thing you need to do is store the PDF in some online store, and now you have very less data, and then you can apply the online resolution function when the member visits the platform. You can apply you can resolve what is the configuration you want to apply, and then you want to score. And that's what we show over here. So so depending on what the parameter is, let's say you resolve it to x alpha and some value of x alpha and x threshold, then you would basically apply the decision function, and then make a decision whether you want to send a notification or drop the notification. So let's look at the library design. And most so like we discussed, this all of this is offline, in the sense like these are like this is a Spark or a Hadoop flow, and the client MP is aggregating the metrics and calling the optimization package. Now let's look at the package itself. So internally within the package, we basically have two main abstractions, and one of them is function fitting, and its job is to basically output a posterior distribution. It's written in a way that currently we use Bayesian optimization, but we could use neural networks. And basically it's going to output the interface is defined in a way that it outputs a posterior distribution, which is used by the next step, which is the optimization module. The optimization module currently we use Thompson sampling, but we could use another algorithm over here like expected improvement or QEI. And the output of this whole thing is a probability density, which is used by the client flows. Let's look at some of the abstractions or some of the entities that we have in this package. Uh, so the first one is task, and task is nothing but a single unit of the problem that you want to solve. The task can contain optimization tokens, and what an optimization token is really an objective or a bunch of constraints, and a given task can have multiple of these optimization tokens. A utility segment, which is which encapsulates all the information for modeling a single latent function fk. So you can imagine if you have let's say a given objective and a few constraints, and if for a given objective you want to model only one latent function, then you have one utility segment per optimization token. But that said, you could have multiple utility segments for a given optimization token. So what it really means is, let's say if you want to maximize sessions, and you can further decompose by saying the maximization of a sessions could be decomposed as maximization over the sessions for each individual distinct cohorts. And now you want to model a separate latent function on each of these cohorts. And we'll get into some of these uh, ideas in the next talk, where we'll talk about how did we enhance the vanilla Bayesian optimization, and some of these ideas that we applied in our production systems, so which basically enables us to not search for one global hyperparameter, but search for a hyperparameter for individual cohorts. uh, and then there is an observation data token, which is used to store observed data. So this is like purely observations. So like the raw matrix y, which is a vector, the hyperparameters x, which is a matrix, because let's say if you have two hyperparameters, then if you have multiple configurations, then it's a let's say you have 10 configurations, and the hyperparameters, there are two hyperparameters, then you really have a 10 cross 2. And then the sample size, so how many members are exposed to a particular configuration. Yeah, let's look at the class diagram, and this is just a high level, where on the left hand side, like we discussed, there is a task which contains optimization tokens, which is an interface, and which implements an objective and a constraint. And the optimization token itself can have multiple utility segments, and each utility segment will have an observation data. Uh, let's look at the visualization and how do we visualize the solution. So, what we have over here is a plot where you have a configuration value on the x-axis, and in this case, the configuration value is threshold, and we call it in-app threshold. And as you can see, there are different values over here, and what you see over here is there are four lines. I think the red line is hidden. Uh, and Let me describe what it means. So the red curve is the true observed metrics. It's pure data that we observe. And then there are three blue lines. And the middle blue line is basically the mean of the Gaussian process estimates. And the surrounding two lines are basically the Gaussian process variance. On, so as you can see, the send by generated is a metric which has a very low variance. Uh, yeah. And we are using JFree chart over here, which is an open source tool to plot to look at these visualizations. Let's discuss some of the results. Uh, so we look at the results over here. This is on the feed experiment, on the feed product that we did. And as you can see, there are two control models. And the goal was, can we, if we reduce the feed sessions by, let's say, 1%, how much can we gain on the viral actions or job applies? And as you can see, in the first case, we are able to improve the viral actions by 3.3% by having a loss of zero point 0.8 feed sessions. And in the other case, we really don't lose a lot, but we get viral actions of 1.2% higher. And the job applications are also higher in both the cases. Uh, And so, what really this package is, it's about operational efficiency. So, for example, throwing out some numbers, feed model tuning needs with this package now they need 0.5x traffic. So, let's say previously they were using 10% traffic to tune their models, now they need 5% traffic. And this improves their tuning speed by 2.5x. Similarly, for the ads case, the tuning time improved by 4x, and for notifications, the tuning time there was an improvement of 3x. So there are a few key takeaways. Uh, so basically, this package using this library, you're able to remove the human in the loop, and it is fully automatic to find the optimal hyperparameters. It improves the developer productivity, and you can scale it to multiple competing metrics. And the onboarding cost is relatively easier, and currently it's used by a few teams at LinkedIn. Ads, feed, notifications, and PYMK. And I think we have gone through most of these examples through this talk. In the next session, Cyrus will discuss about some of the extensions we have built on top of whatever we have discussed thus far. Thank you.